The broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone. It's 1 o'clock, so we're going to get started. Thanks for joining us today. I'm Kelly Pirtle with the NOAA Communications in Norman, Oklahoma, and I'm also a member of NOAA's Central Region Collaboration Team, and I'll be facilitating today's webinar. Today's 3-minute Thesis webinar has been organized by the NOAA Central Region Collaboration Team as a way to increase knowledge and awareness of the work that we're doing in specific areas, in this case, severe weather. This model is a format used by universities across the country as a way to briefly share information about a project, an initiative, or research. Let's go over our outline for the day. Each presenter you will hear from will have 3 minutes, only 3 minutes, and 1 slide to cover their topic. You can see from the list we have a variety of topics and presenters about severe weather from both NOAA research and National Weather Service operations. We'll hear about this year's tornado season from Patrick Marsh, and as he'll provide an overview, and then Kevin Deich will describe a specific event. Scientists Eric Rasmussen and Matt Flournoy, who got up close and personal with the storms this spring, will describe their field research throughout the plains. And our NOAA researchers are constantly improving the tools forecasters use to predict and monitor severe weather. Cody Berry will discuss the NOAA hazardous weather testbed, and Kristen Calhoun will share her latest research regarding lightning. What happens when you work difficult weather events or even find yourself in the path of a storm? Christina Crow and Kim Clockow McLean will share their knowledge and research on critical incident stress and vulnerable populations. You have a chance to ask questions. We will have time for questions from the audience in between each section. If you have questions at any point during the presentations, please submit those in writing using the questions pane of the GoToWebinar. Bethany Perry, the coordinator for our NOAA Central Region Collaboration Team, will collect them for our Q&A sessions throughout the time when people are speaking. I'd also like to acknowledge Jeff Zeltwanger, who is providing our technical support. The good news is we are recording today's webinar, and it will be available for viewing by anyone unable to attend. This is our first time doing this, and we'd love to get your feedback. At the end of today's webinar, please take a moment to complete a very brief survey. During today's presentation, everyone except the presenters will be in listen-only mode. If you experience technical problems, please use the questions pane of the GoToWebinar control panel. I think with that, we're ready to begin. So we are pleased to kick off our first section with 3 speakers, starting with Christina Crow, a master instructor with the National Weather Service Leadership Academy located at the National Weather Service Training Center in Kansas City. She will be addressing critical incident stress.
Thank you, Kelly. So this topic is a little bit different maybe than some of the normal topics you hear about severe weather. We often talk about the science of what we do at Weather Service, a lot of meteorology talk and more about the social science of communicating it. But one question is, have you ever thought about the science of what's happening to you when you work a high impact event? So to start us off, I've got these 2 pictures here side by side of 2 different types of things that could cause you stress. One is you're out for a nice little hike in the woods and you encounter a bear on the trail. Another one is you're sitting at the warning desk and you've got a major tornado bearing down on one of your communities. So my question for you is, what do you think? Is the reaction your body has to these 2 different kinds of stress the same or different? Jeff, if you'll click to the next thing. Surprisingly, it is actually the same. Your body reacts to both of these kinds of stress the same, even though your brain recognizes the difference of the threat to you versus someone else. Your body triggers that fight or flight reaction. It's your sympathetic nervous system that does this. And what it does is really gives priority to your body's survival mode things. So things like your heart rate increases to get that adrenaline so you could run away. Your vision kind of tunnels in on what you see as the main threat, and you lose track of other things going on around you. And what's interesting is that there's been a lot of research from first responders and military folks about these kind of reactions. And they term it as critical incident stress, is that type of stress that you encounter when you see these big events. So Jeff, if you'll click again, they've noticed there's spectrum of types of stress from the experience, from forecasting, in our terms, forecasting before it can be working the operations, the long hours, then it's surveying and all the damage experience that you have at the end. There's also the spectrum of how you are able to manage that stress. It could be related to the severity event, how much you're exposed to it, if you've had several events you've worked in a row, or how you've been managing the regular stress in your life. So Weather Service is kind of looking at this to try to figure out how to help address it, especially as we go into more DSS. And we're trying to make efforts to manage and make this more culturally acceptable to talk about, because part of our mission has to also be caring for ourselves so that we can continue to care for others and serve others. So we're developing a lot of training here at Weather Service and working with different programs within the agency. And I invite you to learn more about this topic and really ask yourself of how are you managing your stress and how can you make it part of your role in our mission. Kelly?
Thank you, Christina. I want to point out that a handout is linked at the bottom of the control panel, so you can go there to learn more information. Our next presenter is Patrick Marsh, the warning coordination meteorologist from the National Weather Service Storm Prediction Center here in Norman, Oklahoma, and he will be sharing a recap of a very busy 2019 severe weather season so far.
Thanks, Kelly. So 2018 was actually a very quiet year in terms of tornado fatalities. And in fact, there were only 10 tornado fatalities in 2018, and there were no violent tornadoes recorded. So contrast that with what happened this year so far, in which we've had over 1,300 tornado reports so far this year, 556 of them occurring in the month of May. And so the way this figure is laid out is the red tornadoes are all the tornadoes this year that are not in the month of May, and the black tornadoes were the month of May tornadoes. So you can kind of see just how active May was. A couple things of importance to note regarding the 2019 severe weather season is we ended a stretch of consecutive days without a violent tornado on March 3rd. There was a violent tornado, an EF4 tornado in Lee County, Alabama, that killed 23 people. This was the first violent tornado in the United States since April 28, 2017, the longest stretch in the NOAA tornado database record. As I mentioned, there were 23 fatalities associated with that tornado, most of them associated in rural parts of Alabama outside the Smith Station's location. Fast forwarding to the month of May, which is kind of the big part of the year, the last 2 weeks of May were almost unprecedented. Going back to 2003 was the last time we saw such an active 2-week period in terms of numbers of tornadoes. In May of 2019, we had 556 tornado reports. This is the most number of tornado reports in any month of May on record, and it's the second most number of tornado reports in any month since April of 2011. We had 13 consecutive days with at least 9 tornado reports. This is a record. I believe it was 11 days was the previous record, or 11 or 12 days was the previous record. The biggest tornado day in the month of May was Labor Day, Memorial Day. There were 77 tornado reports, which by far the most on any given day. One of the tornadoes that I do want to highlight occurred on May 22nd. There were killer tornadoes in southwest Missouri, and this is of note because May 22nd is the anniversary of the Joplin, Missouri tornado that occurred in 2011. So it's a very sensitive date for the region. There were killer tornadoes in the area that continued into the overnight hours, with an EF3 tornado that hit Jefferson City, Missouri, and it's a success story for the Weather Service that there were 0 fatalities with such a strong tornado that occurred in a metropolitan area at night. And a subsequent speaker will speak more about that. So in summary, in total number of tornado fatalities we've had this year are 38, which is high compared to the last couple of years. And prior to that, and 7 of these tornadoes occurred in May, which is a success story to the Weather Service, given how many tornadoes we had in the month of May. So that's a 3-minute overview of the tornado season so far.
Thank you, Patrick. And as luck would have it, today the Storm Prediction Center has a moderate risk up in Minnesota and Wisconsin. So I know you're busy with that, Patrick. Next up, we have Cody Berry, the Executive Officer for the NOAA Hazardous Weather Test Bed, and she will tell us about the test bed's latest activities and research.
Thank you, Kelly. NOAA's Hazardous Weather Test Bed is both a physical space and a framework to develop, test, and evaluate severe weather forecast and warning tools and techniques. The HWT is a joint facility managed by the National Severe Storms Laboratory, the Storm Prediction Center, and the Norman Weather Forecast Office. The goal of the HWT is to accelerate the transition of advances in forecasting and warning for severe weather to National Weather Service operations. NOAA's Hazardous Weather Test Bed is divided into 2 programs, the Experimental Forecast Program and the Experimental Warning Program. The EFP's Spring Forecasting Experiment is held for 5 weeks each spring to evaluate the use of convective allowing model ensembles as guidance for the prediction of severe convective weather. Model output are examined and evaluated daily, and experimental forecasts are created and verified to test the applicability of tools in a simulated forecasting environment. The Experimental Warning Program focuses on the detection and prediction of severe weather hazards. Each spring, the GOES-R and JPSS programs support the Convective Applications Experiment. During these 5 weeks, experimental products associated with GOES-R and JPSS satellites are evaluated by National Weather Service forecasters and broadcast meteorologists alongside standard operational data and products. This year, several single and multi-radar products developed by the Radar Operations Center were included in the experiment. The probabilistic hazard information, or PHI experiments, allow National Weather Service forecasters to assess a new tool using rapidly updating hazard probabilities. These experiments test concepts related to human-computer interaction while generating rapidly updating warnings and storm-based probabilities. The long-term goal of this effort is to move the refined concepts and methodologies into hazard services. In coordination with these experiments, our PHI end-user experiments focused on broadcast meteorologists and emergency managers. Broadcasters receive the products generated by the forecasters and perform typical job functions under a simulated television studio environment. Emergency managers discuss the products in tabletop exercises and use them for decision-making in functional exercises. Within the next 12 months, we are planning 4 PHI-related experiments in the HWT, one for which we are currently accepting applications. Many experiments in the HWT are funded through competitive grants supported by NOAA's Office of Weather and Air Quality. In addition to the experiments already mentioned, we anticipate 2 experiments related to forecaster use of vulnerability and warning comprehension data and hazard simplification. You can find out more about the HWT online at the website listed, and follow us on Twitter at NOAA_HWT.
Thank you, Cody. We will now take a few minutes to address some of the questions submitted from our audience. And again, don't be shy. You can type your questions in the questions pane of the GoToWebinar control panel. Bethany, do you have some questions?
Yeah, thanks, Kelly. The first question that we have is for Patrick. And the question is the busy tornado season this year related to climate change?
That's a really good question and one that I'm being asked quite a bit. In short, the answer is we don't know. In order to assess the causal mechanisms that we're seeing with some of what we're seeing in the tornado trends, we need a much longer data set. And right now the tornado database is actually fairly limited when you consider that tornadoes are rare in space and time. So the short answer is we don't know yet, but I know that there's quite a bit of research ongoing within the academic community, and that includes NOAA collaborators on trying to assess what impact climate change is playing in what we're seeing in terms of the longer term trends with the tornado database.
Thank you, Patrick. Appreciate that. Christina, the next question is for you. The question is, how can someone find out more information about managing critical incident stress?
So the handout actually is really helpful, I'd hope, for folks. There are some one-pager handouts for employees, for managers, for families of workers, for tips and tricks of things to look for, things to do. There's also some training modules on there that for people to learn a little bit more, and they can also talk to folks at EAP, the Employee Assistance Program, or there is a disaster distress hotline for folks who want to have a conversation with like a mental health professional about situations that they're dealing with disaster stress. And as a note on that, is also that just the hotline is available for non-government employees. So like families, friends, survivors you encounter on a damage survey, things of that sort.
Thanks, Christina. It sounds like there's a lot of resources out there for folks to turn to. And then Cody, there's a couple questions for you about the hazardous weather testbed. First, how are participants chosen?
For the spring forecasting experiment, applicants are selected by National Weather Service leadership in each region. For the experimental warning program, each PI has different research priorities, so the researchers prioritize the applicants by number of times previously applied without success, their schedule availability with regard to when their projects are taking place, and then the applicant interest statement. They also try to balance across the different offices and regions of the National Weather Service.
Great. And then how long has the hazardous weather testbed been working on these various experiments?
The testbed in general dates back, a very long time. I actually think Kelly might be able to answer that better than me. I think the late 90s to early 2000s.
Yes, it started in a little side room, almost a broom closet, next to SVC operations in our old building. So it's been over 20 years.
All right. Well,
Patrick, I'll ask Patrick a question. Are you still on, Patrick?
Yes.
Okay. What was the strongest impression you had about this last spring? What's something that you will always remember?
So we've had big outbreaks in the past, and we've had big active time periods in the past. I mentioned May of 2003 earlier, in which what a lot of storm chasers refer as the 2 great weeks of May, where it seemed like chasers were always chasing. But what was unique about this one is typically whenever you have big severe weather outbreaks, the atmosphere needs to take a day or so afterwards to kind of reload and get the moisture and the ingredients back in place. And we really didn't have that this year. The atmosphere was able to do this day after day after day for essentially 2 weeks, which is something that I'm certainly going to take away as being unique, is that we never had the down day, the recovery day that we typically see with these prolonged outbreaks.
Yeah, it was an interesting time in May for sure. All right, thanks for answering the questions. Those are great questions, and you still have a chance to send questions. If you're in the audience, just type them into the questions pane of the GoToWebinar control panel. We'll now transition to our second section, starting with Eric Rasmussen. He is a research meteorologist with the University of Oklahoma Cooperative Institute for Mesoscale Meteorological Studies, and he works at the NOAA National Severe Storms Lab. He was one of the principal investigators for the very successful Taurus project this spring. Taurus stands for Targeted Observation by Radars and UAS of Supercells. And they roam the Great Plains, basically. Eric?
Thanks, Kelly. This Taurus experiment was a joint project of NSF and NOAA, and we did, as Kelly said, this last spring very successfully, thanks to the atmosphere mainly, and we'll be doing the same experiment again next spring. The domain for Taurus is shown in that inset in the upper right on your screen. Basically, the plains everywhere from the mountains east to where it gets hilly. So what are we trying to document and why? In this cartoon on your screen, it's a cartoon of a supercell, and the gray area is the precipitation region. And then I've got some black lines that represent where we think boundaries may occur near the ground in these supercells, may help to focus rotation. But the important thing here on this cartoon is that kind of green translucent arrow that goes from the lower right up into the storm, and it's marked with big bold letters. So if you start at the bold letter A in the lower right of the cartoon, in our forecast experience, we know that we can analyze and forecast that environment out there pretty well. We know what the storm relativity is in the K-bar to a pretty good confidence. What we don't know is what happens as the air moves towards the letter B, where the supercell starts to accelerate it. And that increases the storm relativity and the low-level bulk shear and all these things that are important for tornado production. And then as the air passes on into a supercell toward that letter C, it starts encountering precipitation and cooling, and that can increase the low-level spin of the air, especially about a horizontal axis. And then it appears in our observations and in models that the air then turns abruptly southward towards a low-level updraft where a tornado could potentially form. And it probably has something to do with all those boundaries that are intersecting down in that part of the storm. So what we want to understand is the chain of processes from that letter A to D. And how can we go from that well-forecast and well-observed environment and determine if a tornado is going to form or not? And so, for example, with that kind of new knowledge, we can develop much better predictors in our CAN models like the HER, and then the currently used updraft helicities that we all use. On the time scale of warnings, maybe we can identify certain precipitation configurations up near C that could lead to that enhanced low-level spin inside the storm. And that may add 10 minutes of real useful information to the warning process. And then maybe we can use the radar to identify certain features down in the rear flank of the supercell near the letter D, which would tell us, yep, that rotation is going to be turned upward and develop into a low-level mesocyclone and possible tornado, or no, that air is going to skim on by and not become involved in the tornado process at all. So in Taurus, what are the observations we're making? The big purple plane is the NOAA P3 Hurricane Hunter. It gets 4D dual Doppler analyses of the storm throughout the life cycle of the storm. We've got UAVs, the two red aircraft flying below 2,500 feet across those boundaries with low-level surface mobile mesonet instruments in 4 vehicles nearby. And finally, there's 2 mobile Doppler radars. They're doing mainly vertical scans through those boundaries to show us what the fine detail is on those boundaries. So by combining all these measurements in Taurus, we want to understand those processes along that green arrow that could improve our forecasts and warnings. And that's all I have.
Thank you, Eric. On a side note, we do have the hazardous weather testbed history on the NSSL webpage. Thank you, Vicki Farmer, for sharing that. And the collaboration goes back to the 1980s, actually. So we'll now hear from Matt Flournoy, a doctoral student at the University of Oklahoma, who was also involved in the Taurus project. He will talk about a new type of ballooning used for the first time.
Awesome, thank you, Kelly. So like Kelly said, my name is Matt. I'm currently a PhD student at the University of Oklahoma, and I had the pleasure of working in the Taurus campaign this past spring, and specifically I was in charge of leading the wind sonde mission. So to answer probably the main question in your head right now, what is a wind sonde? Well, there's one pictured in the bottom left-hand corner of the screen there for you, and it looks like a styrofoam cup, because the nice thing about the wind sonde observing platform is that the whole thing weighs about 12 grams, which is really light, much lighter than the typical weather balloon radio sonde packages launched by the Weather Service and during research projects. And it does fit inside of a styrofoam cup. That is the wind sonde right there. So because it is so much lighter, the balloons, the size of them that is required to lift it into the air is much smaller. So this enables us to perform different research missions with these balloons, as opposed to ones that can be performed with the larger scale radiosonde weather balloons. So what you see pictured here is a picture of our most successful windsonde mission from the Taurus Field Campaign. The student there, Maddie Diedrichson, an undergraduate student at the University of Nebraska-Lincoln, is currently in the act of launching a windsonde. So the goal here for this mission was to get ahead of the storm in our pickup truck with the balloons already pre-inflated and the windsonde instruments already locked onto GPS coordinates, so everything's ready to go. And we jump out of the truck, and all we need to do is attach them with zip ties and then launch them up into the air. So the goal is to have them be just buoyant enough to lift up off the surface and then enter the storm at low levels. So specifically, the feature of the storm that we're most interested in observing with these windsonde instruments is that low-level cloud band that you see right behind Maddie there, indicated by the red arrow. So that may be indicative visually of some of those storm scale boundaries feeding into the low-level mesocyclone and possibly into the near surface circulation and tornado vortex itself. This has been observed, this has been noted in high resolution numerical simulations, but we still don't know how this works exactly in the real atmosphere and in real supercells. But it is thought this airflow and that associated cloud band is thought to increase tornado potential via some mechanism. So the goal of the windsonde mission is to get ahead of that cloud band and storm scale boundary and launch 7 or 8 weather balloons into it, performing an effective storm relative transect through that region so we can better sample that layer of the atmosphere. And again, this is something that has only been done once or twice before in recent field campaigns. So the data that we're collecting here is invaluable and quite rare. Maddie has spent the summer researching it, and preliminary results suggest very interesting storm scale features happening there that will ultimately, with more research, help better our tornado forecasts and better predict supercells and tornadoes. Thank you.
Thank you, Matt. I want to add that the Taurus project is one of the things highlighted in the most recent NOAA story map. It was a story map focused on the activities in Norman, and you can get that on NWSTC. Find that, it's really good. Next up, we have Kristen Calhoun. She's a lightning expert and research scientist at the NOAA National Severe Storms Laboratory. And Kristen will talk about the Global Lightning Mapper and show us why flash size matters.
Thanks, Kelly. Yeah, I'm going to talk about the geostationary lightning mapper that's on the new GOES satellite. So before I get into what that shows us exactly and how that shows us flash size, I want to give a short primer on storm electrification. So you get a 1.5 minute, what is normally a huge part of a storm electrification class. So we'll start with that first figure, and it's basically going to show, it shows how charging happens in thunderstorms. So the idea is you get, when you have an updraft with mixed base, you have graupel and small ice colliding, you get charge exchange. And then over time, due to sedimentation and trajectories away from the storm updraft, you get a larger scale charge structure where you have what we consider the dipole or the tripole structure. So that next figure will show kind of what we've thought for years, simplified charge structure where you have a dipole, or in this case, a tripole charge structure with negative charge in the mid layers and positive charge up near storm top and positive charge down below. And what we also understand about lightning is that it initiates where the electric field is maximum. So that's in between your positive and your negative charge. And you have your positive leaders will then break down through negative charge, and negative leaders break down through positive charge. Well, that's a pretty simplified structure of what is actually a much more complex system. So if you go to the next figure is a cross section through what is a supercell through a numerical simulation. So what you see here, the contours give you that charging rate to graupel, depending on where you are. So you have the bounded weak echo region, and just above that, you have positive charging to graupel, and then in other areas, you might have negative charging to graupel. And so when you combine that with also trajectories away from that storm core, you get really small pockets of charge in and around the main storm updraft. And then you get much more of what we consider that dipole or tripole structure when you go out towards an anvil or maybe a stratiform region. So if you go to the next two, I can show you. So in the lower one, you have the small pockets of charge where you have not far for lightning to travel. That would be similar to what it's like near the storm updraft. But when you have something that's more laminar, like the top one, in an anvil, you can get really large flashes. So I'll take you to a real example from the hazardous weather test bed this spring that a forecaster put up on our blog. Next is a 4-panel of reflectivity at lowest altitude in the top left. Top right is the flash extent density from the GLM. Bottom left is the minimum flash area or size from the GLM, and bottom right is the total optical energy from GLM. So in this case, a non-severe case, but you had the leading line where you had a lot of smaller flashes there to the south near Mobile, Alabama, and then you had the lightning extending up pretty far north. We're talking about nearly 3,000 kilometer size flashes out into the stratiform area. And if you go to the animation next, they'll give you an idea of what the forecaster can see from GLM. So now this again is from the MRMS lowest altitude, and you have visible satellite from GOES, and then the total optical energy colored a little bit differently from the GLM. But you see consider the small flashes in the main little core there near Mobile, and then that large extensive flash extending up further north. And I'm sorry that didn't loop for everybody, but you can see it over and over again that basically you get a lot of small flashes in and around the main updraft, and those large horizontally extensive ones going out into the stratiform. And that can have an impact on things like decision support services. Knowing that a big flash can happen, even though it might be a bit rare, you'll know that cloud-to-ground lightning is possible even 3,000 kilometers away from your main core.
All right, thank you, Kristen. That's a lot. This is so interesting. I'm learning so much. I hope our audience is too. We will now take a few minutes to address some of the questions submitted from you all. If you have a question, remember, type it in the questions pane of the GoToWebinar control panel. Bethany, you have some questions?
Yeah, thanks. Matt, the first question's for you. It's, will the observations be matched up, and you have to apologize, I'm not necessarily sure what this means. Will observations be matched up with the TTU K-band radars that are looking to sample? So you might want to also explain that question a little bit to us as well.
Yeah, I can do that. So I think that's referencing the Texas Tech University K-band radars, which are quite high resolution, small wavelength radars that were used in the field, 2 of them during the Taurus field campaign. They were scanning vertically through the same section of the storm that we, the Windsong crew, was attempting to operate in. So the answer to that question is yes. I personally am very interested in comparing Windsong's trajectories and in situ atmospheric observations with the sorts of features that you can see in those vertical scans, vertical radar scans from the Texas Tech radar. So answer is yes to a very good question. Thank you.
Yeah. And then there's a follow-up. What's the cost per Windsong, and what's the realistic max altitude?
Oh, the cost per Windsong, if I remember correctly, Eric can probably correct me if I'm way off on this, but it's a little bit less than the operational cost of a radio sonde, probably around half of the cost. And the maximum altitude that they're capable of traveling the whole depth of the troposphere. We were mainly focused on low levels for our mission, and due to electrification and other problems and icing within the storm, they rarely got up very high. In one weaker supercell that we sampled, I believe that they went as high up as 14 kilometers or so, just to give you an estimate of the upper end that we personally sampled on this project.
Great. Well, thank you, Matt. Next question is for Kristen, and the question is, can you explain the difference in the frequency of small flashes versus big flashes, and how that impacts something like a lightning jump?
Yeah, so the lightning jump is discussed a lot in terms of severe weather and predicting severe weather from storms. And when a lightning jump happens, it's predominantly driven by the small flashes in and around the main updraft core. So what you're getting, very rapid change in those small flashes, you're getting a large charge replenishment in and around the updraft, and so you can just continuously have those small flashes. When a large splash happens, it's much more energetic and it breaks down a lot more charge. Then you could have like 100 small flashes equal roughly to the amount of charge breakdown of a larger flash. But in terms of a lightning jump, yeah, we're looking specifically at those small flashes in and around an updraft. And that's how come a lightning jump can predict the idea that a storm's intensifying at that time.
Well, thanks, Kristen. The next question is for Eric. And the question is, are the mobile Doppler radars dual pole? And the person is interested if you guys are looking at any dual pole signatures.
Yeah, that's a good question. So we do have a dual pole mobile Doppler. That's the NOAA XP X-band dual pole radar from here at NSSL that tries to scan both. It's sort of a sales strategy, the whole depth of the storm, and then more concentration on the low levels. And yes, we definitely will be looking at the dual pole signatures, especially related to what's going on there just to the north of the low level updraft and in an area where the spin seems to be really augmented by the precipitation.
Great, thanks, Eric. And a follow-up to that was, how is the Taurus experiment or experiments different from vortex experiments?
Yeah, that question gets asked a lot, and I actually know a little bit about all the experiments, personal knowledge all the way back to the 1800s. No, I guess it was the 1900s. So that's a fair question because you want to know why we seem to keep doing the same thing over and over. But from my experience, I think Vortex 1 and Vortex 2 were very focused on tornado genesis. And it turns out the actual formation of a tornado is something that seems to happen over the course of tens of seconds and in areas maybe hundreds of meters across. And we simply have not been capable of observing those sorts of processes very close to the ground on very short time and space scales. We wanted to, but I think our experience shows that it's just almost impossible to move the equipment you need into the right spots and get it operating at exactly the right time to catch tornado genesis. So Taurus, we've backed our focus out more to the supercell and the things we can observe. And I think I kind of carry that same philosophy over in Vortex Southeast, where I also do a lot of work, and to try to encourage the researchers to actually observe what's observable instead of maybe observing what would be most satisfying intellectually. We have to get new information and new knowledge out of these experiments.
Great. Well, thank you. Another question, that Taurus made a lot of wind measurements, and I'm not sure, Eric, this one's for you or Matt, but Taurus made a lot of wind measurements, and were there any temperature and humidity profilers as well?
I guess I'll take that, Matt. We did do in a far field of the storm, say out in a 10 to 20 kilometer range and closer to the updraft, we did do continuous. We did frequent soundings. We did spiraling ascent and descent UAV soundings, and we also have a number of in situ thermodynamic observations, such as the ones Matt talked about, and then from close to a half dozen vehicles with mobile MES networks. So, and then there's one other kind of a novel in situ observation of thermodynamics going on. The P3 Hurricane Hunter aircraft, for the first time, was in Great Plains experiment, was flying a downward-looking Raman LiDAR. So we'll get a whole curtain of thermodynamic profiles in the few thousand feet below the aircraft, going back and forth in the info all day long.
Great, thanks, Eric. And Kristen, there's a question that came in for you. What's the most surprising thing you've been able to see with the new GLM?
I think the surprising thing is those large flashes. I know it surprises a lot of forecasters, and we knew they occurred. We just didn't know how big some of those flashes have been in terms of in the stratiform and out into the Anvil region. So it wasn't that long ago that we discovered that lightning could initiate out in an Anvil and come back towards the storm core, but it's just seeing how frequent that happens. And I think, as one forecaster said earlier this year, that he's never going to mow his lawn again under an anvil, just seeing how much lightning's actually going on in those.
Oh, wow. All right, thanks so much. Matt, the next question's for you, and the person would like to know if you have any results from this year's mission, and then what are your plans for next year?
That's a great question. So we do have, like I said, Maddie has been working on the preliminary results so far this summer for part of her Hollings project as an undergraduate. So long story short, we've only been able to look at the data for a few weeks, but we are seeing probably some evidence of those storm scale boundaries that we're seeing in numerical simulations. At least near the surface, we see cyclonic wind shifts in the airflow that's flowing toward the tornado and low-level mesocyclone in the tornado cases. Aloft, it's much more complicated, and there are many features, both dynamically and thermodynamically, that we'll need to analyze further before we can say anything more conclusive there. I'll just say real quick, one of the key aspects of this that we want to look at too is the thermodynamic data aloft. We can retrieve some kinematic fields aloft above the surface using radar data, but it's very hard to obtain in situ measurements of the thermodynamics. So that'll be something crucial that comes out of the WinSOND data analysis. As for next year, we hope to continue the WinSOND mission in accordance with the Taurus 2020 plans as well. And hopefully we'll have even more WinSONDs out there to be able to deploy into these storms and get a better sense of kind of the airflow of what's going on north of the low-level mesocyclone and or tornado.
Thank you, Matt. Thank you. Also, Kristen and Eric, those are some great questions and good discussion. We'll now begin our final section, starting with Kim Clockow-McLean. She is a SIMS scientist and leads the Societal Impacts Research at the NOAA National Severe Storms Laboratory.
Thank you, Kelly. So I'm going to be talking to you today about societal research on vulnerable populations. And this is a topic that's coming up now pretty frequently when events occur and people perish, especially tornadoes. That's the focus of my talk today. This happened on March 3rd this year in Lee County, Alabama, an event that Patrick provided an overview of. And also May 25th in El Reno, Oklahoma. That was another high-profile event. In both of these events, we had a particular kind of vulnerable population, people living in mobile or manufactured homes. And so we saw some high fatality counts in those events. This topic comes up because the Weather Service mission, saving lives and protecting property, is implicitly behavioral. And in that, our success as an agency depends on what people do with our information. It's for this reason that our field has increasingly embraced behavioral scientists and social scientists like me. And the way that social and behavioral scientists go about tackling this problem is first to sort of envision a process model and then tackle that and try to figure out where something is a problem and how to fix it. So we see, the Weather Service sends out its forecasts and warnings to the public. This sort of nebulous blob of the public is something that we then break into different groups. We can do this in many different ways, but one that's quite common is by vulnerability or the propensity to experience different kinds of outcomes in tornadoes. I showed 3 example different groups here of people who experience very different kinds of outcomes when these events occur. On the left, you have people who live in more well-built structures or people who are high information seekers, have access to a lot of different technologies, maybe are quite weather salient, and these people tend to fare very well when tornadoes occur. But we see different kinds of outcomes for different groups. People who live in manufactured housing see some of the highest rates of fatality by exposure, but also people who perhaps speak English as a second language. All of these different kinds of groups and more are shown to have different kinds of outcomes. So a question that naturally arises is, well, why is this and what can we do to help meet the needs of these populations? So what we're looking for when we examine these groups is all of the essential elements of successful warning response. The model of that is at the bottom. We see that to successfully respond to a warning, people must receive it, they have to understand it, believe it, personalize it, and have the means available to them to respond, and actually know how to respond as well. When we look across all these populations, we see that different populations may have challenges at different points in this chain. And as we go about our process then, we kind of are behaving similarly to the medical field in that we're first looking to come to a diagnosis. What is it that is a problem in particular for these groups? And then we can devise a treatment. So broadly in this way, we're creating a kind of capability in tornado epidemiology. This is something that's an ongoing activity here at the lab and something I'm personally very passionate about and my leadership is very passionate about. And we're doing quite a bit of hiring to try to get the skills in place where the researchers are very skilled at each of these steps in things like behavioral science or things like communication, all of these antecedent components of the response chain, so that we can really get to the heart of how it is that the vulnerable populations need to be served. Thank you.
Thank you, Kim. For our final presentation, we will hear from Kevin Deich, the Warning Coordination Meteorologist at the National Weather Service Forecast Office in St. Louis, Missouri. He will discuss the devastating tornado that hit Missouri's capital city just a few months ago.
Awesome, thank you, Kelly. And yes, May 22nd was quite an evening for us here at the Weather Service office in St. Louis. For those of you that don't know, Jefferson City is the capital city of Missouri. It's in central Missouri. And a little background of this tornado began around 11 p.m. just southwest of Jefferson City in a town called Eldon, and then moved northeast and reached Jefferson City around 11:40 p.m., covering a path of about 30 miles long. The picture on the left there actually shows a tornado as it was entering Jefferson City, and that picture is taken off of a video. And it's an interesting video because the lady is kind of looking for the tornado, and you know the lightning wasn't lighting it quite right, and then all of a sudden one does, and you can actually hear her audibly gasp. It's a very eerie video, but scary nonetheless. We did issue a tornado warning with about 40 minutes of lead time for this tornado, and then with about 10 minutes of lead time, we actually upgraded to a tornado emergency, and this was the first tornado emergency our office has ever issued. Which was pretty remarkable for this event. So why was this event a miracle? Well, we didn't have any deaths. You think this time of night, you know, a lot of people are home, a lot of people are probably asleep, but we had no deaths, which is truly a miracle. I think one of the reasons was because this tornado actually hit a lot of commercial buildings. It hit a car dealership, it hit some restaurants, and so that time of night, nobody was in those buildings. So that was part of it. But then another part of it, and this story, when I tell it, it still gives me chills. The picture on the right was a mobile home park. There are about 6 mobile home trailers there. And as you can see, there are none left. And the one straight ahead is in the trees there, and there are a couple that we couldn't find at all. So how do these people survive? Well, there is an owner, the owner of the mobile home park has a house, which is directly behind where this picture was taken. And he tells everyone when they move in that on nights where there might be severe weather, he leaves his basement door unlocked for them to take shelter. Well, sure enough, 6 people on this day heard the tornado warning, heard the tornado emergency, ran out of their trailers and into this gentleman's basement and lived to tell the story. So it truly is a miracle, and then that guy is truly a hero because I truly believe he saved 6 lives that day. So with that, I am finished and we'll open for questions.
Thank you, Kevin. That really is an amazing story of a man helping his neighbors. We have some time left that is our final presentation. We have some time left to address your questions. So go on and enter your questions in the questions area of the, along there on the right-hand side. Bethany, do you have some questions?
Yeah, thanks, Kelly. Kevin, there's a question for you about what it was like to survey that tornado and whether there's a lot of media attention, and then specifically how you got into the affected areas.
Sure. Yeah, it was quite a bit of media attention. It was actually really organized. The Jefferson City Police and the Cole County Police had the whole path pretty much blocked off to public access beside the people that lived there. And they had a rallying point for the media. So we had a police escort that actually took us anywhere we wanted to go within the damage path. It was one of the most organized, damage surveys that I've been on. But one kind of neat thing too was because we had the police escort, we stopped in the command post, where law enforcement, fire were all gathering, and the Jefferson City mayor was there, and she gave a really kind of heartfelt, emotional speech about everyone that was there helping her community, and it really was seeing the devastation was terrible, but kind of rallying together and seeing the community come together was really special.
Thanks, Kevin. Appreciate that. Kim, there's a question for you. Can you give an example where efforts to address the needs of a vulnerable population have been successful?
Yeah, so a lot of the work we're doing at the lab is still ongoing, but a really great example I've seen actually comes from within the Weather Service itself. It was an effort made to look at deaf and hard of hearing populations in South Texas. This was Trevor Boucher's work, and he really went through the process of meeting with those populations and understanding, doing this diagnosis phase I described, where he found that certain kinds of messaging from the Weather Service, including when thunder roars, go indoors. It didn't reach those people because they couldn't hear the thunder roaring. For them, they really needed to have something that spoke to the visual cue. And so he worked with them to come up with new kinds of strategies that met their language and met their abilities, and in that way helped improve service to that vulnerable population. So I thought that was, while that was, maybe not as much of a complex, meaty, thorny issue as something like housing and tornadoes, where we have a multifaceted problem and a lot of resource needs that'll go into the solution. It was a great innovation, and really excited to see that kind of work coming up within the Weather Service as well.
Thanks, Kim. And there's another question that just came in for you. When research suggests that protecting vulnerable populations will be most effectively accomplished through policy changes, for example, social welfare programs, how can researchers communicate those findings in a scientific and persuasive manner?
That's a really interesting question. I think we have to be mindful that there is a difference between science and policy. One can inform the other, but they aren't the same. Where I tend to fall on that is we find for some vulnerable populations, resource needs is a really big part of the picture. I think the best thing that we can do is to be just honest brokers of that information. We can try to offer the policymakers the variety of options for addressing the problem. There are times when resources just aren't available to increase funding for something, and it might be best to come up with some other kind of short-term fix to try to address the need in the short run, and to see that ideal policy outcome as a long-run solution. So that's something to keep in mind too. Sometimes there can be a temporary, something you can try for the short run, and then look to the long run to build out something that maybe takes a lot more resource.
Well, thanks, Kim. And with that, let's go to some open questions for all of the panelists. And you'll see all of the names on your screen. If you have any more questions, please don't hesitate to put those in the box on the column on the right. And in the meantime, let's go to a question for Cody. Can you describe the atmosphere of the hazardous weather test bed? What's it like to bring together people from all of these different backgrounds?
It kind of varies experiment to experiment, and also sort of with the personalities of those that are in the group that is visiting for the week. We have some that can be sort of very quiet and focused, whereas other groups can be a bit more rambunctious when you're working with, say, broadcast meteorologists. They have big personalities and are really chatty, and so that's a sort of a completely different environment than from what the actual physical room with the Weather Service forecasters can be like. So it really varies, but it's a lot of fun, and I have not heard of anyone walking away disappointed in their experience.
Thanks, Cody. Eric, question for you. What was the most unusual thing weather-wise that you saw in the field this spring?
Oh boy, there's a couple of things that stand out. One was the day of the tornadoes west of Canadian Texas in late May. I can't remember the date exactly, but it was just a bizarre day because the low-level humidity was so high that we were in fog and drizzle just ahead of those storms, which I just don't remember seeing in other tornado experiments. And even as we went in to intercept the low-level mesocyclone, it was just sort of a uniform low stratus. We really didn't have any cloud features until suddenly we saw the tornado about a mile away from us. So that was really unusual. The other thing that stands out in my mind about this last spring is we actually collected a nice data set on an anticyclonic supercell that wasn't simply a left split off of a right mover. It was a storm that formed as a left mover and maintained anticyclonic rotation, and actually just looked like a mirror image supercell. So that was pretty unusual and fun.
Well, thanks. Kristen, the next question is for you. Can positive strikes generally be assumed to be more powerful than negative strikes, or is it more complicated?
Yeah, it's more complicated than that. And generally speaking, yeah, a positive CG has a higher likelihood to get into those really high kiloamps, like 300 to 500 kiloamps. And negative CGs tend to be more in like the 10 to 20 kiloamps. But that doesn't mean a negative CG can't have problems. I think when we talk about fire starts, it's not just the kiloamps, but it's the continuing current that sometimes happens with the positive cloud-to-ground lightning that can contribute to like fire starts. Hopefully that answers it.
Yeah. Well, and a follow-up question, can you describe the longest flash that you've seen with the GLM?
So there was a study, WMO had a study published which they put together the longest flash seen prior to the GLM. I know now we have seen multiple flashes that have eclipsed that. And so just with the GLM, and we're talking about there's one example that Lockheed Martin likes to show of a big squall line moving across the central United States, and it triggered a flash that extended up from kind of western Missouri down across eastern Kansas into Oklahoma and down into Texas. I'm not sure on how many kilometers squared that is, but that was all a single flash that went across multiple states.
Wow. Well, thanks for that. And Kevin, you'll get the last question of the day, and especially considering how active this season's been in your personal experience, and as a warning coordination meteorologist, what is the tornado and or severe weather advice that you give to your friends and family?
Well, that's a good one. Really just to pay attention. Have multiple ways to receive warnings. I think a lot of people rely on their phones. Well, if you lose cell phone service, then what do you do? So have redundant ways to receive warnings, and then have a plan. A lot of people have a plan, but then when do you enact the plan? So it's great to have plans, but make sure that when the time comes, when the Jefferson City nights come, to go ahead and enact the plan that you've made.
Okay, that's very good advice. Thank you, Kevin. And that wraps up today's 3-minute thesis webinar on severe weather. Thank you to all of our panelists today. At the end of the session, there will be a few brief questions that will appear on your screen. Please take 1 more minute to respond to these. Your feedback really is crucial to help us plan future webinars, especially since this is the first one. And we'd like to know if you have more than one person participating from a single registration. Shout out to the Radar Operations Center. I know you all are listening to this in your conference room, so thank you. And if you're like them at your location, let us know. As a reminder, this webinar was organized by the NOAA Central Region Collaboration Team. If you'd like to learn more about what that is, check out our webpage at www.regions.noaa.gov/central. If you have any questions, please contact me, Kelly Pirtle, KELI.PIRTLE@noaa.gov, or Bethany Perry, BETHANY.PERRY@noaa.gov. Thanks again to everyone for your participation, and have a great day.